So again, hello everybody. Thank you for coming and for this second part of the lab, which will be a bit more of a game, hopefully fun. So a few words about it will work today. As you know, we will have 13 speakers, and they will give a 2-minute talk each. And the feedback mechanism, we will call it the Caledonian feedback because it's what Bonnie uses in her graduate schools. And it works in this way. So Luisa will go around with this traditional, homemade, very good local biscuits. And, can you hear me? In any case, no? You couldn't? Should I start again? It's working at least. Okay, can you hear me? Fine? Good. As I was saying, feedback for the speakers. Luisa will go around with these cookies, and you should pick one. Please do not eat it. You will see a number. And so please pay attention to speaker number, that number. And then you have time, after this lab, during the week, whenever you want, if you want, you go to your speaker, hand in so as a gift. So you give the biscuit as a present, and you will tell him or her a very good thing about his or her talk and something that can be improved. So the speaker, when the speaker sees one of you coming with a present, they should expect something very nice and something they can improve. So this is the feedback mechanism. And we have 3 feedback for every speaker. Okay, we have 39 cookies over there. So this is the feedback mechanism. And if any one of you speakers wants a private feedback from me or from Bonnie, just ask it after the seminar. Otherwise, this will be the feedback. Okay? And then we will have an ice-breaking thing at the beginning that Bonnie will explain. After that, there will be our sequence of speakers, 2 minutes. And when the 2 minutes expire, we will wave. And after 30 seconds, we will stop the speaker in any case. So we are sort of softening it, but in any case, at 2 minutes 30, we will stop the speaker. And I think that's it. So we have already uploaded the slides when there are slides.
Questions?
Sorry?
And questions?
Questions, okay. So there is time for just one question. So after each talk, if you want, you can ask, the public can ask one question. And that's all. You can go.
Okay. And just for those of you who are looking at the cookies, they look very tasty. I've tried some already. Give them to the speakers, but we have some spare cookies at the back table there. So for those of you who are going to participate as the audience and give feedback, we have a little gift and reward for you as well. So please do. I'm told that they have nuts and various things in them, and there's a sign that says, "Be aware." I was thinking, attack cookies, but actually they're very delicious. So we have that at the back. And so we should actually pass them round now. Yeah, so Louisa's going to come round and you can take it. So please do, everyone. Also, if you don't have a cookie to give to a speaker, please do give feedback to any of the colleagues that you see speak. And it's a gift to have feedback. So always start with one positive thing and then something they can improve. Lisa. So very helpful. Yeah? What happened?
Anybody has number 14?
Yeah.
You can eat.
Ah,
6 minutes, 9.
Because number 6 is not.
Okay, so
Didn't
So let's
Okay, so
alphabetical order. The 6 is probably easier, so that it is easier to. Okay, mine is 6.
okay, so I probably all the six
Yeah.
pull together. Yeah.
This will be a good networking opportunity for all the 6s and all the 9s to find each other and
I
decide
will find it.
half and half. There we go. We need one more.
Any 6 or 9 around?
Yeah, but this one's area 9.
This is the other problem.
Okay. Bonnie, do you want the
Can people hear me? I'm used to shouting, so that saves the microphone for others. Okay, so the people have worked very hard to prepare and practice for this 2-minute talk. And actually, anyone can do it. And in fact, all of you are going to do it. So that is our icebreaker and start. We've had a lot of listening to wonderful talks all these last 3 days. And it's time for some dynamic movement. And so you're going to all, you can come back to your seats, but in the first event of the afternoon here, I'd like you all to, once I explain things, get up and move to the spaces around the chairs. And you're going to find a person that you haven't met before, that you haven't talked to, and that you haven't explained about your research or anything to. So a new person that you're going to meet. And I'm going to ask you to speak for 2 minutes about your research. And then the other person will speak for 2 minutes about their research. And it's a conversation just between the two of you. And it's a really useful skill to have, because when you come to a conference like this, it's very important, yes, to present your paper and your seminar, but the most important and valuable thing about a conference and a school is actually all the wonderful people that you meet. And you never know if the person that you meet at one of these schools becomes a lifelong co-author, colleague, which has happened to many of us in the Cortina summer schools. And you never know, as a young researcher, if the person that you meet, who you think, oh wow, I am so impressed with this person, that they might actually be impressed with you and might be able to offer that post or that job in the future, and you might end up working together. So having a 2-minute, here's all my research, talk with people to see if there's a synergy is really, really useful. So we've given you a structure. So this is what we do to ask our PhD students. Actually, on the very first day of arrival at the graduate school and our university. So they have very little PhD development to start off, but they have some idea of why they've come here and what the project is going to be about. And they do this. So we all can do this. So you talk about the broad area of your research. What is your topic area of research? 1 or 2 sentences. Well, here, most people are involved in celestial mechanics. So you can be a little more special to that. What is your research question? The key focus that you're going to explore. So what is a little more detail about the project that you're working on? How are you exploring it? How are you going to explore it? And then, why is it important? What value does it have to the world, to yourself? What impact will it have? Well, sometimes, if it's applied, we see clear impacts. And sometimes it's because it's a puzzle, and I've solved it, and you're all excited about that. That's really loud for our area in mathematics as well. So you have these 4 questions to answer in 2 minutes. And so I invite you to get up, and I'm going to time it. And when you hear me shout 2 minutes, then you change over to the other person. And then 2 minutes more. And so you'll get a sense of what it's like to speak for 2 minutes and distill the essence of your passion for your research project. Does everybody understand? Yeah? Nod your heads? Yes? You ready? Okay. Go back to the back. Okay. And I will say, make sure everybody has a partner. And then we can start. Now I need the microphone because everybody is excited and buzzing with conversation. So has everybody got a partner? There's no one else left alone? If you are, put your hand up and we can find someone. Excellent. Okay. So we have quiet. I'm going to set the timer. And when I say go, 2 minutes of the first person. So you all know who's going to speak first? Okay. Silence. Silence. Okay. Go.
Stop, 2 minutes. Okay, now you swap round with the same partner, and the other person starts when I say go. Stop you. Right? Everyone, that's 2 minutes. You have to stop now. Everyone, give yourself a round of applause, because that's a very hard thing to do. So, big clap. In the UK, we call that research speed dating. So you've just been speed dating. In the next few days, if you want to meet some new people, just say to them, oh, can we just play this game and I will tell you my research for 2 minutes and you can exchange. And it's a nice thing to do. And it's not going to be scary anymore because you all know how to do it. And you can go and talk to a total stranger and find out all the interesting things you do. No! No, you have to pick up an extra one there at the end of the day. We still have some work to do. Okay, so if you want to go back to your seats, now we're going to hear the prepared presentations. Thank you, everyone.
Funziona che quando non ci sono slide di chi parla, mettiamo la slide della lista grande, così vedono anche il numero. Ah, ok. E altrimenti metti la slide. Grazie.
So, as Anna said, I can shout now, you guys are quiet, good. And as Anna said, the protocol here is we're going to have time for the 2 minutes and listen. We've understood the feedback mechanism. To have things go nice and speedy, Anna's going to chair and invite the people up. They will have the 2 minutes. I have my timer, just like I did for you guys. And I will not go beep, 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 beep at 2 minutes, because that's terrible. I'm just going to wave at them if they go past 2 minutes. And if we go past 2 minutes, 30 seconds, I will stand up and say stop. But we hope that we get just within 2 minutes. And so I will let everyone know how long it took. And it's quite an achievement to do this in 2 minutes. So at the end, we will have one question, and then we will applaud because it's a big, important thing to do. And it's always good to thank the speaker in applause after the question. And I said to the speakers, part of the performance is to accept the applause, to accept the good wishes of the audience. So that's part of the performance. So I hope that you will follow that and enjoy the day.
Okay, thank you, Bonnie. Our first speaker, so speaker number 1, is Rafael Alves Silva. I don't have a title, but you will maybe give a title.
Hi everyone. Well, the main subject of my work is the study of mean motion resonance at planetary systems. I focus on developing a model, analytical model, completely analytical, using classical expansion techniques, series expansion through, well, Taylor expansions and Fourier expansions, and obtaining classical quantities like the Laplace coefficients and Hansen coefficients, and then I managed to compute these things inside a script, and well, well, I managed to first I started with a 4 degrees of freedom system in a 3-body problem, general 3-body problem. I consider the basic case a planar case, and through these expansions I reduced the system to 2 degrees of freedom and managed to separate the secular part from the resonant part of the problem. And well, that's the main part of my project, of my work. That's why I think this is important, because I managed to separate these 2 things. And I think I went too fast because that's it.
Okay? 1 minute, 39 seconds.
Okay.
Okay, thank you, Rafael.
Should I
Any questions for Rafael?
No questions? At all? Okay.
Okay, so Louisine Bradel.
Yes.
She's number 2.
Thank you. Okay, so I'm going to try in 2 minutes to make everyone interested in singular symplectic geometry. First of all, what is this? Most people will know what a symplectic manifold is. Of course, it's the basic construction or where everything happens in classical mechanics. Singular symplectic geometry is a very slight generalization of this, where you have a manifold with a form that's symplectic almost everywhere, but then you have a hypersurface where you have some problem. Either the form becomes degenerate, or you get one of these blow-up singularities, which is called a B-symplectic form. Hopefully the formula makes it a bit more clear. Now, why would anyone care about these abstract objects? Well, it turns out in certain coordinate transformations that happen in celestial mechanics, usually during regularizing transformations, these things can actually pop out. So your transformation isn't canonical, and your symplectic form gets transformed into something that looks like one of these. So this provided a motivation to try and look at what dynamics would look like on a manifold of this type, and then hopefully when we're done developing a bit of theory, we can go the other way and maybe get some interesting results from this. Okay, so.
1 minute, 19 seconds.
Okay, wow.
So thank you very much. Any questions? Okay,
Is
can
there
you, yeah, you have
any application to the regularization of collision that you have this?
Okay, so they've popped out in a couple of very classical transformations, like the Levi-Civita, regularization, and some of the McGee coordinate changes. But so far, we haven't got enough into the theory to be able to apply it back. So this is what I'm hoping to do for my PhD, but I've just started.
Very good.
Thank you.
Excellent. Thank you again.
Okay, so that one is Christoph Berger, and I don't remember the title because it's not there. So. I research terrestrial planet formation and collision physics.
So, thank you very much. My name is Christoph Burger, and as you already mentioned, my work is focused on terrestrial planet formation and collision physics. What we do are, you've already seen this before in my presentation, what we do are SPH simulations of individual collisions, including self-gravity, sometimes also including solid body physics, especially for smaller bodies where material strength becomes important. My personal interest when it comes to these collisions is the fate of volatiles, especially of water. This is related to questions like the origin of water on Earth, or how water is delivered to terrestrial planets in the habitable zone of extrasolar planetary system, things like that. You can see an example of my work in this nice animation here. What you see is a collision of two water-rich planetary embryos, a relatively low, so a relatively central impact, a mass ratio between the bodies of 1 to 2, a quite slow collision, 1.5 times the mutual escape velocity. And both of these colliding bodies are covered in water. The larger body, we call it the target, is covered in blue water particles, but it's all the same. The projectile in white water particles. And already from this one animation, from this one simulation, we can learn a lot. Like you can see, or you can probably not see very easily, there is a lot of, especially this volatile material, spread out through space. And this is material that is lost in this collision. There is also material transferred between the bodies. This is when the one body plunges through the other one and accretes some of the differently colored stuff like that. What we want to do eventually, our long-term goal is to include these individual collision results with respect to water into the next generation of n-body planet formation codes to model the collisions that are currently modeled not at all, usually in them, more accurately and better. Thank you.
1 minute, 48 seconds.
Okay, thank you. So I suppose that you already Christoph, just in case someone has a question.
Oh, sorry. 12 seconds.
Any question for Christoph? He already spoke this afternoon, but if there are further questions for him, please.
Could you provide us any detail on the details of the actual computations, the computational effort, and the
To give you an idea, is the NSPH hydrocode, in case you are not familiar with the SPH method, then let's talk for dinner until tomorrow morning. We run them on, so these are hydrodynamical simulations, we run them on GPUs to speed up the things, so graphics processing units. And one simulation takes about 1 day. What you saw in this video, for example, there were 100,000 SPH particles included, that determines the resolution, and these particles are simply interacting with each other. Just if you had a grid code, but it's a Lagrangian hydrocode, so that means that's what we are going to talk about after dinner.
Thank you.
Good.
Thank you.
Thank you.
Okay, so Josué Cardoso dos Santos, and this number 4, and we will talk about translatory motion dynamics through intermediaries.
Hi, hello everyone, I'm Josué. I'm not talking about two potato problem, it's two body problem. But as you could see, I couldn't finish, I'm sorry for not finishing the presentation before. The idea of this study is to apply these dynamics on two problems just like moon, Earth coupling, just like Pluto, Charon, binary asteroids, binary stars. And the idea is that this problem is not solvable in terms of analytical equations, and we try to build these canonical techniques, canonical models that are able to provide analytical models of the problem. And we use different techniques just like elimination of the nodes, generalized elimination, intermediaries. And on doing that, we're able to find two kinds of models that are able to be representing the system very well. And the simulations are evolved for 500 orbital revolutions. And despite of this long time, all the variables are still in good precision. So what we will interfere in your choice is because the model without elimination of the parallax will not require this canonical transformation, but you need to integrate in terms of elliptic functions. If you want to integrate it easier in terms of trigonometric functions, you can use the parallax elimination, the second model that we're studying here. But you have to pay the price of performing a canonical transformation before that. So we hope to evolve, include more forces and more terms on the disturbing potential here, and in order to have these models used for future application in space missions, for satellites and other celestial systems. Okay, thank you.
1 minute, 49 seconds. Well done.
Any questions for Joshua? No? No questions? Okay. So, Mauricio Misquero, speaker number 5, and she will talk about planar periodic orbits arising from the Schubert-like orbit in the Caledonian symmetric four-body problem, which is already 2 minutes, probably the title. I don't know. Please.
Yeah. So hi everyone, I'm Mauricio Misquero. I'm working on the planar periodic orbit that arise from the Schubert-like periodic orbit in the Caledonian symmetric four-body problem. First of all, what's a Schubert-like orbit? So this is a one-dimensional symmetric collisional orbit that exhibits simultaneous binary collisions of pairs of bodies on both sides of the system center of mass, which is then followed by another collision of the inner bodies at the center. My research is concentrated on extending that orbit on a plane in order to produce a family of planar periodic orbits. In order to do so, I consider and solve the Caledonian symmetric four-body problem. This problem has specific initial conditions that the body starts on the line and they originally have only transverse components of velocities. It also has symmetries in time and about the center of mass. By using angular momentum of the system as a parameter, I generate the family of equal mass planar orbits that start from the Schubert-like orbit and go all the way until the semi-choreography orbit, and then with reversing of the motion back to Schubert-like orbit. I also analyze the linear stability and vertical stability of these orbits. On top of that, I aim to extend my study by considering the cases of unequal masses and the Caledonian symmetric five-body problem by introducing the fifth stationary body at the center of mass. And I hope that the periodic solutions that I search and analyze will help in extending the knowledge of the dynamics of the general problem. Thank you.
1 minute, 47 seconds.
This is too short.
It's excellent.
Okay, any further questions for Valerie? She already spoke yesterday, but if there are any more questions for her? Questions over there? No? Everything was
I have this.
Yes.
This I asked yesterday, but didn't understand. The photo in the middle, the picture in the middle, is 2D or 3D?
All of them are planar. All of them are planar.
Ah, okay. So that's.
Oh, well, excluding the first one, of course.
Yeah.
Good. Good. Okay. Thank you, speaker.
Okay. And now we. Where are we? Yeah, there. Number number 6 is Gladstone, Duarte Ferreira from Barcelona, and we will talk about modeling Potherma's dynamics.
Good afternoon. My research now in University of Barcelona is understanding the mechanisms of a comet called Potherma, which has a special type of dynamics with Jupiter. Here's Jupiter's orbit, this black, and this red here is Potherma's orbit. And at some point, they approach each other, and Jupiter's like putting inside. It has it beginning an orbit further from the sun, and then it starts to make an orbit nearer the sun, and then again Jupiter takes it outside, in the outside region. There is a paper in 2000 by a group of professors in Caltech, including Jeremy Marsden, who model this problem as a planar restricted circular three-body problem. And it's a really nice job, it's a really nice paper. They do it all qualitatively. They claim that the mechanisms for this jump are connections between stable and unstable manifolds of the Lyapunov orbits around L1 and L2. But their paper is qualitatively. So when we did this to Potherma, we got the data from Potherma and put it in the model, and we were forced to do some type of adjustment so that this jump could appear. So we are trying to investigate now. The next step is this, the planar circular, the best model, or maybe we can use the eccentricity or the third dimension of the problem so that we are not forced to do the adjustment. Thank you.
Exactly.
You told me that I had some 50 seconds, and I was like, 5 seconds, 15 seconds.
Any questions for Gladstone?
Didn't understand if your approach is analytical or numerical.
Semi-analytical, in principle, semi-analytical one. We use some computer algebra computer algebraic code to do this manifold computation and everything.
Is a limit cycle that one?
No. It's just the orbit around between 1910 and 1980.
Okay.
It's not.
Okay. Thank you.
Thank you.
Okay, so number 7 is Pano Kumar. And the title is Georgia Tech and JPL is Jet Propulsory Nebula. Okay, cannot say it. Summary of work.
Hello everyone, my name is Banu Kumar. I'm from the Georgia Institute of Technology. I'm a math PhD student working under Rafael de la Llave, and just going to briefly summarize my work at GT and at JPL. So at Georgia Tech, I'm kind of just in the beginning phases of figuring out my research, but I know the basic problem I want to solve is how to design space missions that use little fuel. So for this, some of the tools that, based on my reading, seem somewhat promising would be stuff such as intersecting invariant manifolds, using Arnold diffusion, and normally hyperbolic invariant manifolds to find good unstable pathways along this. So that's my work at Georgia Tech. In addition, ever since I've been an undergrad, I've been also working in the radio science group at the Jet Propulsion Laboratory. It's a NASA center in Pasadena, California. And there, so radio science basically is doing planetary or solar science or physics experiments using the radio system on spacecraft. So one of the things I did at one point was characterizing the total electron content in the solar corona using the time when the spacecraft was on the other side of the sun and Earth was on the other side. And we were able to, using several years of data, show that the magnitudes of the changes we saw we're roughly in correlation with the 12-year solar cycle. Other than that, it's a lot of code I've written to do various tasks, helping with data processing and whatnot. So, any questions?
1 minute 42.
Any questions for Manu? No questions? Thank you.
Oh, here's one.
Oh, yeah, there is one.
Do you have a favorite mission of the missions that have been launched, or do you have a plan for a? Do you have a kind of mission you would like to plan?
One thing I personally have, I mean, I'm more on the engineering side than the science side. Out of the existing missions, I'd like to say one of Voyager or Cassini. I'm not sure which one.
Okay, thank the speaker.
Okay, so Mauricio Castro, number 8, and the title is Resonance Tones in the Linear Sitnikov Problem.
Okay, hello everyone. I'm Mauricio Misquero Castro and I'm PhD in the University of Granada. And I'm going to talk about the resonance tones in the Linear Sitnikov equation, which is that one. And the resonance tones are in the diagram. The Linear Sitnikov equation is an example of a Hill's equation, and that is a second-order linear and periodic equation. In this case, depending on two parameters. One of those is the lambda parameter, which is positive, and the other is an eccentricity parameter corresponding to a certain ellipse determined by R of T and E. The resonance tones are the instability regions of the equation in the space of parameters. What I've been working on is in the qualitative description of the diagram, and I found that there are some unusual tones and unusual features we have explained from an analytical point of view, and from a global approach, because we don't focus only on eccentricity that are close to zero, but the whole range of it. We apply this diagram to some generalization of the Sitnikov problem, which is that animation. That's the classical one. We apply to some generalization. For example, we prove the existence of symmetric and periodic solutions of that kind of problems. Thank you very much.
Okay. 2 minutes exactly.
Any questions for Mauricio?
Which kind of tools are you using to face these problems, like this search for periodic or
Which kind of tools? What?
tools, mathematical tools?
Oh, you mean analytical or?
More precisely.
Okay, precisely. For example, in the.
I guess analytical.
Yes, analytical.
So which kind of analytical tools?
Analytical. Well, for example, a special change of variables and also can I see
The slide.
Yeah, for example, when we approach to the eccentricity one, so I've applied some theorems of the literature. So it's been more like to putting all the information together, all the theorems that I have available and apply to this problem. that's why you were asking for. So
Yes, I was asking which for example, which theory?
oh,
Which kind of
okay.
theory?
Okay,
Those
in the framework of Hill's equation, there's a lot of tools that you can use, and yeah, more or less that.
Okay.
Okay,
Thank you,
you.
Steve.
Okay, number 9 is David
The
Sarocco.
first one? Okay, there is
And the title of his talk is Multi-Satellite Missions, Acquisition Strategies for Formation Flying.
It's working. Good afternoon, my name is David Sarocco. I'm a mathematician from La Sapienza, and I will present you what I've done on an internship on Thales Alenia Space. As you can read, it was a work in multi-satellite missions, acquisition strategy for formation flying. In this case, acquisition means the dynamical process that brings satellites put on some random position on a reference orbit to a specific one that it's needed to accomplish a mission. So we have the launcher that releases, for example, 3 satellites, and because of errors of the launcher, of the accuracy of the launcher, probably they will be not on the correct nominal geometrical disposition. So what I've done, it was to the question was how to bring these multi-satellites from the launcher release point to the nominal operative position. In this case, how in general means strategies to optimize fuel consumption and or time. In my case, I fixed the time for this orbital transfer or acquisition as you want, and I implemented an algorithm through which, given the starting state of the formation and the final state of the formation, given the time, it gives you the optimal maneuver needed to reach the target. And I developed also an interface in which you put, I don't know where you stay, okay, in which you put the reference orbit for the formation, the relative dispersion of each satellite and the target of each satellite, and you start the simulation, okay? And then you can see at the end the error in velocity and position because of the perturbations that are not modeled in the algorithm, but you can put on the propagation after the algorithm give you the optimal maneuvers.
Okay. 2 minutes, 20 seconds.
Questions for David? No
What?
questions for David. Well, okay.
What optimization algorithm did you use?
It was a discretization. It was the equation was the Hill equation, and through Pontryagin theorem, they applied the Pontryagin theorem to a discretization of Hill equation. So they found the costate at the initial state, and through which, with an iteration method, they solved the state equation.
So you're trying to optimize time and energy together?
Sorry, the optimization was on the fuel consumption.
Just on the fuel consumption?
Yes.
Okay.
I think we have time for Christoph questions.
Have you tried to apply results to the terrestrial planet, find a mission or singular planes? Because as far as I know, this was...
I don't hear you.
If you apply your results to the terrestrial planet, find a mission, singular ones, because I think one of the reasons why it was realized was that it was so difficult to keep this formation right.
I'm not sure I'm understanding your question. If I apply my results to other...
Not to the terrestrial planet, find a mission.
I don't think it's related
Don't
to...
know if the answer is properly.
No, but I don't think it's related to the planet, which I... The question is if I apply these results to other planets?
No, to the terrestrial planet finding mission. That was a proposed NASA mission for information and information.
Okay. No.
Okay.
Okay.
Thank the speaker.
Thank you. Okay, so Daniele Serra, number 10, about orbit determination for interplanetary space missions.
Thank you. Hello everybody, my name is Daniele Serra from the University of Pisa and I am a postdoc researcher there. So, I am working on orbit determination for interplanetary space missions. For those of you who are not familiar with space missions, it's all about a planet and then usually an orbiter, so a spacecraft orbiting it, taking measurements and sending it to Earth, so always in communication. I am specialized in radio science experiments where the measurements that the spacecraft takes are the range, that is the distance from the spacecraft to the Earth, and the range rate, which is the radial component of the velocity, so the radial velocity. Yes, why do we do that? We determine the orbit of the spacecraft, of course, but we are mainly interested in determining other parameters, which characterize, for example, the planet. And in this case, since I am mainly involved with the Juno mission to Jupiter, which is currently going on up there, we are interested in determining its gravity field and some other parameters such as the love parameters concerning the tidal effect of its Galilean satellites, for example. How do we do that? We use a software which we started developing in Pisa like 10 years ago, I think, when I wasn't working there, of course. So, and it's very important because the software is called Orbit 14, and it's very important because we can have measurements which are we obtain results which are independent from results obtained with other software, for example, Monty, which is the software used at JPL. Why do we do that? Why did I choose this with this field? Well, determining the gravity field of the spacecraft, of the planet, of course, will give us information about the interior of the planet and so information about its origins. And ultimately, of course, it will help answer the question, how did the solar system form and why is life on Earth? Thank you.
2 minutes, 30 seconds. I was about to stop you. Okay.
Thank you, Daniele. Any questions for Daniele?
Have you actually gotten any results yet? Important results from your radio sense experiments?
Yes, we did. We published the first preliminary results for the even gravity field in last February, and we also analyzed the data from two gravity passes, from the last two gravity passes, and we're about to deliver some other results very, very soon. Also about the odd gravitational field, so the non-symmetrical part.
Thank you.
Okay. Great. Thank the speaker.
Okay, now we have number 11, and this Danilo Stella speaking about data analysis, a business intelligence platform.
I am Danilo Stella. I'm from the University of Rome Tor Vergata, and now I'm currently working at the GEOS, which is a joint venture between Italian Space Agency and Telespazio. And now I'd like to speak a little about data analysis. The interpretation and how to give value to a huge amount of data is one of the main problems of the last few years. One of the principal approach is to build a BI platform, a business intelligence platform, and with a data warehouse. The first step is to extract data from very different data sources. For example, database, sensor, or satellite data. Satellite data because EGEOS own a lot of Earth observation data. For example, Cosmos Climate data. And we are really interested in satellite data. And extract this data and then put them into a standard data structure, which is called data warehouse. After we put this data into a data warehouse, we can build reports or even dashboards for user or clients. The most important thing is that we have a great increasing of the speed of when computing this data, because they are very, very huge and they are very, very different, because we work with satellite data, which are images, or we work with databases data, which can be everything you can think. And now, data warehouse and in general BI is a very, very important branch, and every IT company has their own data warehouse product.
Very good. 1 minute 58 seconds.
Questions for Danilo? So I have one. What is business intelligence exactly?
Business intelligence is this procedure. A data warehouse, which is quite a black box here, and it's a data storage technique, which is quite complicated to speak with in a few minutes. So I have to consider this data warehouse as a black box, and speaks about what we have at the beginning and what we want at the end. Because the question is, I have a great amount of data, maybe I have a dataset full of data. I have a dataset with years of satellite data, and I don't know what I can do with this data.
But why business intelligence? Because they are oriented to business, to trade something, or
it's business. The name.
Yeah,
the name.
yeah.
The name, because the first year, this was born for manager and high level statistics. So you can choose with a BI platform. They choose the path of the investment. So this was the reason, but now it's quite different. I'll do such this.
Thank you.
Okay. Thank the speaker.
Okay, Jarka. So number 12 is Jarka Sukschilik. And the title of her talk is a 120 celestial seconds slice from Romania.
My name is Ivarka. My name is a very old Hungarian name, and it means maple. I came from Romania, the land of Dracula, and I always dreamed when I was a little child that I will become an astronomer. My dream comes true because now I'm working as a scientific researcher at the Astronomical Institute in Romanian Academy, where I have 3 topics. The main topic is celestial mechanics, the second is archaeoastronomy, and the third is teaching in astronomy. In celestial mechanics, I started with regularization method, and I continue with the symplectic method, periodic orbit, stability, study in restricted 3-body problem, in Caledonian 4-body, 5-body problem. The latest research, what I made, with Galilean satellite motion, I realized that the Earth is not perfect, and I made a lot of mistakes. And yes, and archaeoastronomical research, in archaeoastronomical research, I studied the alignment of some necropolis building elements from mostly from Neolithic, which helps the archaeologists to make a better view about the Neolithic culture. By the way, you know that the churches from San Martino was aligned. The third is the teaching in astronomy. Started with a question from my daughter who said, Mama, what do you do? And I tried to answer, and this answer from astronomical point of view, I write it in a book which has the title Teaching Astronomy for Small Kids. So keep walking, as Johnny Walker said. Thank you for attention. Thank you. Okay, so any questions for Yasha? We're running away.
Here, for answering your question.
I don't know if this one works actually.
Maybe? Okay.
Yeah.
So 2 minutes and 28 seconds. Any questions?
Okay, so the church in San Martino is aligned with what? You said it's aligned with
Yes,
something.
astronomically aligned. Yes,
With
with the solar motion, with solar motion. It's aligned because it's between the solar arc, this apparent motion of the sun on the earth.
Okay. Thank you.
Okay, great. Okay, thank the speaker.
Okay, and our last speaker, what is... Okay, give me.
Hello, good afternoon to all of you. Myself is Tiwari from Indian Institute of Technology, ISM Dhanbad, India. At first, I would like to thank the organizing committee and Department of Science, organizing committee of SBSM 2017 and the Department of Science and Technology for providing, Government of India for providing me the financial support to attend this school. My topic is computation of halo orbit, which is a periodic orbit. At first, it was introduced by the Robert Farquhar in year 1968. In this halo orbit, the first mission was ISEE-3, launched in year 1978, and then followed by a SOHO mission in 1995. And ISRO is also planning to launch a mission named as Aditya L1 mission. For details regarding the Aditya L1 mission, one can follow the link provided here. And so I have computed the halo orbits in the restricted three-body problem in the Sun-Earth system, taking the account of the radiation effect of the Sun. We obtained that the time period of the halo orbit gets increases with the effect of radiation pressure. Including the effect of radiation in the model, we get the more accurate and precise result we observe. And so, and now I am working on the horizon, and we want to compute the numerical computation of halo orbit, and using in Bain 24 we transfer trajectory. I am still working on that. Thank you.
1 minute, 37 seconds.
Any questions? Yes, one.
So the work on halo orbits that you're doing, is that for Aditya or
No, I'm not doing
just
for
generally?
just academic. I'm for my PhD. That's why I provided the link.
Okay.
I'm not.
Thank you.
Okay, thank you, speaker.
Okay, so thank you to all the speakers, and I must say that it was surprisingly good as a performance, because it was very difficult to say something in 2 minutes or less, and you managed to do it. Actually, I could have managed to do it in my in my couple exercise before. So really congratulations to everybody, and I hope you will get satisfying feedback, and thank you again for coming.
I'm just going to say, don't forget, a thank you to all of you. In the audience, there are the biscuits at the table at the back there. They're very good. So thank you to all of you. It was fantastic. It's fantastic what you can do in 2 minutes.
Lunch. Yeah. May I see the name of the second speaker to give it to him? It's Bradelli.
For us, who are like in the beginning, it's like, okay, we only have the 2 minutes to talk about it.
So you have to stop the number 2. You have to stop